Welcome to my video series on declouding my life and repatriating my data to a server hosted in my home. This video series will cover the entire build and setup process as well as ongoing maintenance. Now, why would I want to do this? If your data is on another man's computer, is it yours? I don't think so, especially if you don't pay that man for a hosting service. If it's on my hardware in my home, then it's my data. I'm opting out. I'm opting out of surveillance. I'm opting out of training somebody else's AI model. I'm opting out of being a product. I'm opting out of being profiled. I choose to opt out. I want agency over my digital life and my data, and I want to be able to freely communicate with other people without moderation and oversight by anyone else. I want my online freedom back. Now, do I have anything to hide? Honestly, I don't know. Do you have anything to hide? You don't know, even if you think you don't. You don't know what will be classified as unacceptable in the future. No one does. So why have your documents, pictures, emails sitting on some cloud provider's infrastructure waiting to be scanned for something that was acceptable in 2018, but not in 2028? People want privacy to protect themselves from an uncertain future. These are my high-level requirements. All data is hosted in my home. Email and communications are available remotely. I need access to my emails and communications via my phone or laptop. TLS and SSL connections must terminate in my house. This means no proxies will be used between my remote devices and the services I host. I am not looking to break the bank, so it must be cheap and cost-effective. This is the high-level plan I have in mind. My server will be connected directly to my LAN network. I will deploy a Pi-hole virtual machine instance to provide a local DNS server, and Pi-hole will manage block and add and tracking networks via its block lists. A TrueNAS instance will provide a network file share, and I will pass through the 4 hard drives I have planned for the server directly to TrueNAS. In order to host a local email server and have remote access, I need a public IP address. I will use GetPublicIP.com to get a public IP address and direct the public traffic to a virtual machine within my server. This virtual machine will connect to GetPublicIP and then direct the public traffic to the internal server via a virtual network for its given port. This strategy will isolate the public-facing services from my home LAN network. How this works is the GetPublicIP virtual machine establishes a VPN connection to GetPublicIP's server. The public traffic then gets directed through this VPN tunnel to my endpoint. I can then use IP tables to direct the traffic to the required server over a virtual network. I have used static IP addresses for my ISP in the past. However, I've run into a lot of problems with them. In particular, no one likes to receive email from a residential IP address, so they have a bad reputation before you even purchase it. You are also tied to a specific location where your ISP has delivered their connection. The great thing about GetPublicIP is that it does not matter which internet connection you use. As long as you can establish that VPN tunnel, you will have public connectivity. This means if my ISP goes down, I can fail over to 4 or 5G without reconfiguring any services. Or, if I need to move my server to a different location, it's a matter of plugging it in and everything will come back without reconfiguration. One of my requirements is that the encryption needs to terminate in my house. So if my phone or laptop remotely connects to my email server to check for mail, then the TLS or SSL connection needs to start at my phone or laptop and end at my email server. This means no proxies. This is end-to-end encryption. This is how it'll work. My phone will send packets to the public IP address. These packets will then get directed through the VPN tunnel to the endpoint virtual machine on my server, which in turn will direct those packets to the email server over the virtual network. The email server will then terminate the connection. This means that it's fully encrypted to everyone in between my phone and my email server. This setup will also work the same when remote email servers send me emails or use an XMPP chat service or any other hosted service. Let's get started with the server build. I bought a second-hand Cooler Master Silencio 652S case from Facebook Marketplace for 30 New Zealand dollars. That's about 17 US dollars. It has 6 3.5-inch drive bays, filters on all the fan intakes, and sound dampening foam on the panels. It turned out to be a very nice case once it was cleaned up. I dismantled the case and cleaned the parts and then put it back together again, ready for the motherboard. This case can be configured for 2.5-inch drives or 3.5-inch drives. I moved the rails over to accommodate the larger 3.5-inch drives. I only got 5 out of the 6 caddies, but that's okay as I'll only be using 4 of them. I'll keep track of the cost as I go through this build. I have a lot of old parts laying around that I'll be using, so I won't be able to cost up everything. Now comes the motherboard. I really went cheap with this one. I bought a Qiyida X99 K9S Micro ATX motherboard. It comes with 4 DDR4 slots, a LGA 2011-3 CPU socket, 1 PCI Express x16 slot, 1 PCI Express x1 slot, and a M.2 NVMe slot. It was sold with a Xeon E5 2680B4 CPU and 32GB of DDR4 ECC RAM. The kit cost just 163 New Zealand dollars delivered. That's 91 US dollars. The CPU is 14 physical cores and 28 after hyperthreading. This is more than enough for any home server. I will not recommend this motherboard though, and I'll get into the details as I go through this build. First, I'll install the I/O shield in the back. Make sure you hear and feel it click in. Then I'll check the motherboard spacer spacing. As you can see, I need to move 2 of them up to suit my micro ATX board. Now, install the motherboard. I like to pay attention to the I/O shield area first and make sure the motherboard is seated nicely against it, with nothing blocking the ports at the back. Once it fits nicely, make sure all the motherboard screws holes line up with the spacers underneath. I find that the motherboard likes to sit on the spacers with a little play side to side. It has a natural fit to it. Now you can install all the screws. Don't do them up too tight. You don't need much force to keep your motherboard in, and you don't want to crush the PCB. I ended up cross-threading the screw. It jammed in the motherboard spacer and never got tight. Now when I try to screw this out, it ends up turning the motherboard spacer instead of the screw. So top tip, get some pliers and hold the spacer from the back. I grabbed the spacer with my pliers by some thread sticking out the back of the case. Now I can get the screw out and move on with the job. I bought a brand new 550 watt power supply for 80 New Zealand dollars or 45 US dollars. It's a FSP HV Pro and comes with a 5-year warranty. Second-hand power supplies were not cheap enough, and I'm always suspicious of second-hand power supplies. I would rather buy a brand new power supply than deal with a flaky second-hand unit. They are easy to install. Make sure you have them the right way up when you put it in. This case has rubber pads that the power supply sits on, so I had to make sure that they were all in place. Screw it in from the back. Now, I'm going to wrap the 24-pin motherboard power cable with some cloth tape. This cheap power supply has no wrap around the wires and very little cable ties keeping it together, so this will make it look neat. Once done, I'll poke the cable through the grommet to the back side. Next is the smaller 8-pin power cable. It's wrapped and then poked through. Now connect the 24-pin cable to the motherboard. They only fit in one way, so you don't have to force anything in. Then, the 8-pin power cable can go into its slot. This is an AliExpress VTG heatsink bought in August 2019 for $25 US. The listing no longer exists. I have never used it up until now. I don't have the original fans, so I'll use some surplus Be Quiet silent wings I have laying around. It's a twin stack designed for 2 fans. In the box it has some mounting brackets, fan brackets and a small tube of heat paste. First I'm going to mount one of the brackets. Then I'm going to sit the heatsink on the CPU to make sure this heatsink will fit. I had no idea if this heatsink would work, but luckily for me this will work. But before the heatsink can go in, I need to install my Samsung Evo 970 1TB NVMe drive. The heatsink is so big it'll block the NVMe slot, so it needs to go in first. This drive is old and for my parts bin, so I can't give you a price. First, remove the screw on the NVMe slot, then align the drive in the NVMe connector and gently push it into the slot. You can push the drive against the spacer and screw it down. This motherboard did not ship with a BIOS battery, so let's put it in now. I pop the RAM in. Sometimes it's easier before installing the heatsink. Sometimes it's easier after installing the heatsink. The instructions call for the yellow slots to be used first. They only fit in one way, so make sure you feel the click for each retaining clip on each side of the RAM stick. I got some thermal paste from AliExpress. It's MJ M12 and promises 12.4 watts per meter Kelvin, which is a measurement of thermal conductivity. Average thermal paste is between 5.3 to 8.5 watts per meter Kelvin. GamersNexus has an excellent write-up on this. Also, this is AliExpress. Maybe this will meet the specifications. The cost was $5.30 New Zealand, or about $3 US. My preferred application method is a blob in the middle of the CPU and then 4 smaller blobs near the corners. This thermal paste came with a spatula, which I have never used with thermal paste before. I gave it a try and I'm not a fan. It's not needed. 1 blob in the middle and 4 smaller blobs in each corner is all you need. The spatula just ends up removing paste and making a mess. I like to put the heatsink down, apply a little pressure, and then remove it so I can see the thermal paste application on the bottom of the heatsink. This will indicate if I have too much or too little thermal paste. There are 4 holes in the top of the heatsink for a long screwdriver to reach the screws by the socket. I like to get all 4 screws started before screwing them tight. This allows wiggle room to put the screws in each hole. I removed the RAM stick to make it easier to get to the screws. With this heatsink and motherboard, I can leave the RAM stick out until the very end. I tried to use a 3-pin fan that did not have an RPM signal, and the motherboard did not spin the fan up. It does not like 3-pin fans. So I'm using 2 Be Quiet 4-pin fans instead. This is one reason I won't recommend this motherboard, but there are more to come. When you install fans, you need to pay attention to the direction of airflow. Usually, they are marked by arrows on quality fans. You want your fans blown in the same direction when it's installed in a heatsink like this. I also want the hot air from the CPU to blow out the back. I have 2 intake fans at the front of this case to provide fresh air. I also want to orientate the fan so the cable comes out at the bottom on the side of the fan header on the motherboard. This heatsink, like many others, uses a wire bracket to hold the fans on. Hook the fan ends on, then pull it into the slot on the heatsink. This is a fiddly process. I plug in each fan as I go. This motherboard has 2 CPU fan headers on it. I run the excess wire out the back to be managed later. Now I will hook up the case buttons and lights. This is different from motherboard to motherboard, but the concept is all the same. When it comes to the power switch or reset switch, it does not matter which way around the connector goes on. When it comes to the power light or hard drive light, then you have to make sure the positive wire goes to the positive connector on the motherboard. This motherboard has a printed diagram on the PCB and a plus on the header itself to make things easy. If your lights don't work, then try swapping the connectors around. Now I'm going to install the case USB and audio connections. The USB 3 cables terminate to a nice connector. It can only go in one way. The USB 2 header has one pin missing in the corner, so make sure you match up the missing pin on the cable side to the missing pin on the motherboard side. This is a server, and I don't need the audio jacks, but I may as well do it while I'm here. This cable again has a missing pin on it, but it's in a different location. Make sure you match it up again and slide it on in. The case's ports, buttons, and lights are now wired in. This motherboard and CPU needs a graphics card. I had a graphics card in my parts bin, but it did not work. There was no video out, so I had to go out and buy another card. It cost me 30 New Zealand dollars or about 17 US dollars. This was not planned, but oh well. I ended up with a Radeon HD 8490. The front case fans are easy. Just make sure they blow the right way and the wires come out together for easy routing. These Hitachi hard drives came out of an IBM rack server. They are old, noisy, but reliable and fast for a mechanical drive. I have 4 of them in my parts bin and will be using these for a local NAS. After a cleanup, they get mounted into the caddies, making sure the knobs fit into the drive screw holes. Then I can slide them into the case. They have a nice click to it. They are placed in the front fan's airflow, as from my experience they can get hot. Now I can hook up the SATA power connectors. I was going to use spare SATA cables I had laying around, but decided to get new cables instead. I have had trouble with random errors from old low quality cables. The new cables all have a middle clip to retain them and a right angle for the hard disk side. This will make a nice install and should hopefully save time later on from random drive errors. I got the cables locally at 5 New Zealand dollars each, so about 11 US dollars in total. They get plugged into the motherboard in the same order they are mounted in the case. Time for some cable management. Even though this is a budget build, I still like to make it look neat. It'll be easier to work on in the future. This server cost me about 370 New Zealand dollars or about 209 US dollars. The 1TB SSD and 4 2TB hard drives came from my parts bin, as well as a couple of fans, tape, and cable ties. It's as cheap as I can get for something like this. I do prefer X-Lease rack mount servers. They can be cheap, powerful, and a complete solution, but they are really loud and you need a dedicated room and a large rack for them. This server is quiet enough to be in my office and consumer parts will fit it, so it'll be easy to expand or fix in the future. So I had 2 problems. One was the 3-pin fan and the other was a failed video card. Once these were sorted, I was able to boot it up and get it into the BIOS. The build date is very recent. That's nice, and all 32GB of RAM is detected. Now the first thing I like to change is this option. It will switch the computer back on after a power loss, like a power cut. Must have for a server. This motherboard lacks a TPM, but it has a TPM header for an aftermarket module. So this is the next major issue with this motherboard. The CPU temperature is just not available via the BIOS. Looking at the AliExpress listing for this motherboard, it states it does not have a temperature control chip. I don't fully know what this means. Does this mean the fans won't spin up when the CPU is under load? So will this computer have thermal issues? Not that I can see. I ran a benchmark that put the CPU under full load and near its TDP of 120 watts, and it did not thermally throttle. So no, it does not. The hottest it gets according to Linux is 62 degrees. The air coming out the back feels 60 degrees, and I don't hear the fan spinning any faster. If you use this board with a smaller heatsink and case, then you might. I would just spend the extra $5 to have a temperature control chip and have that peace of mind. I would also consider a board with more SATA connectors and PCI Express slots so you can install wireless 2.5 gigabit networking cards or RAID controllers in the future. This motherboard is working fine and is a demonstration of getting a home server up and running on the cheap. Let's continue looking around this BIOS, and I have never seen so many options in a BIOS before. way more than any Dell, HP, IBM, Asus I've worked on in the past. I don't know what most of these options do, which is probably why they are hidden away on mainstream motherboards, but I like having it, even though I will never use it. So this is interesting. I am assuming this is the Intel management engine that us privacy guys really don't like. The BIOS reports nothing is working here. Is this Chinese motherboard based? Let's see if Linux can see the management engine. I will use Coreboot's project's Intel ME tool to have a look. I need to clone the repo, make the executable, and then execute. As you can see, it appears the management engine is not working and is disabled. I wonder if they did this on purpose because they don't like the management engine, or they chose not to invest in developer time to make it work on their firmware. This was an unexpected bonus. I like this motherboard now. Moving on. I like to disable fast boot and quiet boot and set the timeout prompt to 10 seconds because it was really hard to get into this BIOS. Only the delete key above the arrow keys seemed to work. The bottom right delete key never worked. Now I'm going to disable CSM, which is Compatibility Support Module. This enables support for old BIOS devices and operating systems, but it's not needed on hardware from the last 10 years or so. In 2025, everything should be pure UEFI. I need to change the video card from BIOS to UEFI and then reboot, then I can disable the CSM. It's time to install Proxmox, an open source hypervisor based on Debian Linux. It has a nice interface, similar to VMware ESXi, but without the VMware baggage. It's very common in the home lab space. There is a paid option on Proxmox in the form of enterprise repository and support, but for our home lab this is not needed. The install is straightforward. Download the ISO image from Proxmox and then set up a bootable USB stick. On Windows, I like to use a tool called Rufus. You can download it from rufus.ie. Once downloaded, select the ISO image and the USB drive and then away you go. On Linux, there are many ways to slice this piece of cheese. I'm on KDE, so I use KDE Image Writer. It's just easy. Now boot the USB stick and start the install. The first option being a nice graphical interface, and the second option being a terminal-based interface will just work depending on your hardware. I have an old budget graphics card, so it hangs on this screen. Old graphics cards are flaky on Linux. I got around this issue by adding in the No Mode Set option. To do this, highlight the second option and then hit E for edit and then add No Mode Set to the end of the Linux line. This will stop the kernel from setting any fancy graphics modes. Now I can see the installer and move on. I select my SSD, of course. I always use swap, even if I have a massive amount of RAM. If I have 64 GB of RAM or under, then my swap size is the same amount of RAM I have installed. When you get to massive sizes like 128, 256 or 512 GB of RAM, then it becomes impractical to have 512 GB of swap on a fast SSD. So you can always get away with 64 GB, requirements dependent of course. Leaving these fields blank will default to using all remaining disk space. Choose the region, this will ensure the time zone is correct. Set your root password and email address, you can change this later. Set a hostname, it's required, the rest can be left at default. Wait for it to install. Proxmox is now installed and booted up. I'm going to log in as root and then set a static IP address. I'm going to use Nano to edit the network configuration file. My local LAN uses a 192.168.1 range and my DHCP addresses start at .10, so I will use 192.168.1.5. Change DHCP to static. Set the address and subnet mask. My gateway is 192.168.1. The Proxmox documentation calls for bridge configuration. Set bridge port to your Ethernet interface, bridge STP off, bridge FD 0. You can reboot or restart the networking service. I'm going to reboot. Now you can open your web browser and navigate to your static IP address followed by a colon and 8006, which is the port number of the Proxmox user interface. Your browser is going to warn you that it might be insecure. You can safely ignore this message. It means that it's not using a certificate that's been signed by a certificate authority and is normal for local services. You can now log in using your root account. And there you have it, the beginnings of leaving the cloud and bringing your data home where it belongs. This server and this hypervisor will be the cornerstone of declouding myself. Virtual machines will provide me a way to manage different services that have different operating system requirements, sandbox each server in the name of security, implement backup strategies, and so much more. Subscribe and follow me as I configure an email server in my home, my own chat service similar to WhatsApp or Facebook Messenger, file storage and ad blocking DNS. I will also talk about my encryption strategy, networking strategy, backup strategy, and hopefully provide you with ideas for your home server. As for this motherboard, I've been running it for 2 weeks now and no problem so far. This build cost me a total of $209 and excludes the storage, heatsink and some fans. This is fantastic value for money, for the time being. I will keep you updated as I create more parts in this series. Leave comments, good and bad. You won't hurt my feelings. Subscribe and decloud yourself.